Okay, so sorry about that. I forgot to record the beginning, but Ron, you can continue, please.
Thank you. So now we want to talk. We talked about vector spaces, which are the same as vector spaces if there is a linear bijection between them. If we also have a norm endowed on these two spaces, we can also talk about these two subspaces being the same if the norm of the image is the same as the norm of the element itself for each element in V. So now we have another structure that we get to preserve between these two spaces, which is the norm. This is a much stronger. This is much stronger than just the vector space. And if I take another step forward, we can also look at inner product spaces. So for any for any vector space, we can choose a certain inner product endowed on that space. And by choosing it, I can also talk about the linear bijection, which preserves that inner product. So whenever I take two x and y in V, the inner product of x and y, the images of x and y under this transformation T is the same as the inner product of x and y. So there are many ways to answer the question when are two subspaces of Mn, in that case, are the same. So each bijection, we choose it so that certain quantities will be invariant under these maps, meaning that, for example, here is the norm is invariant, here the inner products are invariant, etc., etc. So now I want to talk about another important structure, and these natural maps, the maps which preserve that certain structure, which is the partial ordering on positive semi-definite matrices. I'll explain it in a minute, and the unital and completely positive maps between them. So just a few simple things from linear algebra, and maybe just one definition that undergraduates might not be familiar with, but this is the only definition that might be new to some of you. So let's assume that H is what's called the Hilbert space, but for now it's okay to just assume that it is some inner product space because we're dealing with finite dimensional spaces. So the word complete shouldn't bother you for now. So assume this is an inner product space like Cn with the standard inner product. We denote by B of H the collection of all linear operators from H to itself, which are bounded in that sense, meaning that the maximum amount of how T might stretch a unit vector H is a finite quantity. So for any such operator, we'll soon get back to matrices, and it will be much simpler to understand these definitions. So for any such operator, there exists a unique operator, we denote it by T star, which is also called the adjoint operator, such that for all xy in this inner product space, Tx and y is the same as x with T star y. So for this talk, if we take H to be Cn, just the complex vector space of dimension n, with a standard inner product, B of H is just the space of n by n matrices, right? Because every operator, maybe I'll go to the board, but every operator of this form, which takes Tx and multiplies it by some n by n matrix, is a bounded operator. So in the case of H to be the n-dimensional complex vector space, B of H is just M and C. So from now on, for the rest of the talk, whenever I say B of H, you can imagine that I'm talking about M and C. This will be good enough to understand whatever we're talking about. And in that specific case, whenever A is the matrix I'm talking about, the adjoint matrix is just to take the transpose and take the complex conjugate of each element. Okay, so a few names we have to take upon ourselves, a few definitions before we can go to the interesting things. We say that a certain matrix is self-adjoint if it equals its own adjoint. Obviously, this is quite self-explanatory. So, for example, this matrix here, if I take transpose and the complex conjugate, I get the same matrix. So this is a self-adjoint matrix. Moreover, we say that a certain matrix is positive semi-definite. I might just say positive as we move through this talk. If for any x I take from Cn, this quantity here is always non-negative and real. Like obviously real, but also non-negative. So a simple fact from linear algebra is that A is positive semi-definite if and only if I can find some other matrix B such that A is B star B. Okay, so this is, I think most of you probably seen this claim. This is a very simple claim to prove. So for example, this matrix is positive semi-definite because I can write it as this matrix multiplication, which is just a matrix star times itself. So why are the self-adjoints useful for us? So for any matrix, I have a unique decomposition of this matrix into two self-adjoint matrices, right? Because if I take the adjoint of this matrix, I get the same matrix, and also for this one. So this is sort of like the real part and the imaginary part of the matrix A. So without proof, but this is just for some motivation, again, for why self-adjoints are such a good tool for us. So any matrix can actually be written as a linear combination of exactly 4 positive semi-definite matrices. Therefore, for our uses, if I want to study a certain structure on the matrices, it is very good to just use these basic elements in my space, which are the positive semi-definite matrices. If there is any question, obviously, feel free to stop.
Why we can write it with 4 matrices and not 2 matrices?
So basically what you do is you take the decomposition into the real and imaginary part, and the real part and the imaginary part, if you consider finite dimensional spaces, so these are finite dimensional matrices, so they are diagonalizable. If they are diagonalizable, you can always separate them to the positive eigenvalues and negative eigenvalues, the real and the imaginary part. And overall, you get a certain decomposition of the form positive minus the negative part, plus I, and the brackets, positive minus negative matrix. And all of these 4 matrices will be positive semi-definite. Okay, so this is just a simple construction. It's not really important. It's just a motivation to understand why self-adjoint matrices are really good for us. It's really good to take a look at the self-adjoint matrices, and that's it. Okay, so again, since this space is spanned by the positive matrices, they serve as a great tool to study the structure of the matrix space. So, but what is this structure that I'm willing to present to you? So, we define a partial order on the matrices. Namely, we say that A is a bigger matrix than B if A minus B is a positive semi-definite matrix. Note that A and B might not be self-adjoint at all. They might not be positive semi-definite. For example, these 2 matrices, they are not self-adjoint. If I take the transpose, I don't get the same matrix. But the difference between these 2 matrices is just the matrix. Okay, זה פסה, אבל, יופי, הייתי אחראי. That's good. I was responsible enough to put it here. So the difference between these 2 matrices is this matrix, which has eigenvalues 1 and 0, so obviously it is positive semi-definite. So this gives us a way to say when one matrix is bigger than the other. So this partial order, this is just a simple observation that it is obviously induced on any subspace, just because it only depends on the 2 matrices I'm looking at. And one special kind of subspace, which I'll come back to only at the end of the presentation, is a subspace called an operator system. So this is just a subspace that has the identity matrix in it, and that whenever A is in that subspace, A star is also in that subspace. So if it is self-adjoint, the subspace is self-adjoint and unital, so I say it is an operator system. Okay. So we presented the new structure on the matrix world, which is the bigger than or equal for 2 matrices. So I want to talk about maps which take a matrix which is bigger than another matrix. When A is bigger or equal to B, I wanted to take it to 2 elements which also preserve the same order, that phi of A is bigger or equal than phi of B. So this map is obviously called a positive map. This is a perfect name for such a map, that a linear map from V to some subspace. Note that it doesn't have to be of the same dimension. This could be Mn, this could be Mk, but we say that it's positive if whenever A is a positive semidefinite matrix, its image is also positive semidefinite. This is a mistake, by the way. This is a mistake. This is phi of A, not phi of V. Okay, but whenever A is positive, phi of V is also positive. So let us take a look at one of the simplest examples of positive maps. So let's take a map which takes an n by n complex matrix to the complex field, which is just a 1 by 1 complex matrix, which is defined by the trace. Okay, so notice that A is positive semi-definite if and only if, this is again a linear algebra statement, if and only if it is diagonalizable and it has non-negative eigenvalues. And as you all remember, if A is positive semi-definite, which means that it has non-negative eigenvalues, its trace it's the sum of these eigenvalues. So obviously it is non-negative. So okay, so it has a non-negative trace, which means this map is actually a positive map. This is a very simple example. Okay. But what I'm going to do now, it's to take us a step further, okay? Because we have a certain new structure on the matrix space, but I want to take us to the next level by taking an even stronger structure on these matrix spaces. Okay, so let V be a certain subspace. Okay, we can consider the space which is the K by K matrices whose elements are n by n matrices. Okay, from V. These are matrices of matrices. So we can obviously just erase the brackets, and now I wish I had the board to show you, but whenever I have this matrix whose elements are n by n matrices, I can always just erase the brackets and then look at it and consider it just as an MKN matrix, a KN by KN matrix. Okay, so now we have this new space by taking this subspace and just considering matrices with elements from that subspace. And assume I have some positive map from this subspace to another ML. It doesn't really matter which L it is, but assume it is a positive map. We can define a new map. It's really a very natural map that I can induce from this phi that takes this matrix, again, V11, V1K, every element here is an n by n matrix, and just act with phi entry-wise. Okay, so this again is an L by L matrix. This is an L by L matrix. So this is a new map between two new subspaces, which is induced from this map phi. So if this phi K is a positive map for all K, then we say, and this is a very strict thing to want from such a map, but if Vk is positive for any K, then we say that it is a completely positive map, okay? And moreover, if I take the identity element to the identity element of that specific space, I also say that it is unital, okay? A unital and completely positive map. Okay, so as we can see, completely positive maps are better. They are more strict, but they are, if I find such a map, it is obviously a better map than just a positive map, because they preserve the matrix ordering, and moreover, they preserve the ordering on higher levels. When I consider a certain matrix space of these matrices, this map also preserve that ordering. So this is a much stronger map. But this might obviously raise a few questions. For example, how do you check whether a map is completely positive? This seems like an impossible task. If I want to check that a matrix from a metric space to a matrix space is a positive map, this might be possible depending on the map. It seems like an easy calculation. But to check it for any K might be an impossible task. So how do we do it? Moreover, are there even any completely positive maps? Because as I present this definition to you, we don't even know if such a maps exist, and maybe this is an empty definition, so it won't be interesting. And from the other side, we can ask from the less optimistic side, the more optimistic side maybe, if I take a positive map, why would phi K not be positive? I mean, this is sort of a natural inheritance from phi, so why won't it be completely positive? So as we will see in this talk, these questions actually have some pretty good and surprising answers, especially in the case of matrix spaces. So let us begin with one simple map that we all know and I hope love, that whenever B is a K by N matrix, I can consider this map, which takes me from Mn to Mk, by a conjugation of A with B. Okay, so if A is positive semi-definite, as I said earlier, I can write it as C star C, which means that phi of A is B star C star CB. By the properties of the star operation, I can write it as CB star, which means these are two matrices, a matrix star matrix, okay, which means that phi of A is also positive. Okay, so a conjugation is actually a positive map. But actually, we have a much better result. So let us assume that A is an element in this space, MM of Mn, okay, which is a positive element. Recall that this means that A has the form of an M by M matrix whose elements are N by N matrices, okay? So, by the definition of this phi M, the induced map, if I want to act with phi M on this matrix of matrices, I just act entry-wise. I do the conjugation on each element of this matrix. But using block multiplication that we all know from linear algebra, again, most of the talk will be very elementary linear algebra, I can see that this matrix by block multiplication is actually this phi M here. So this means that this phi M is itself a conjugation by a certain matrix. Again, I regard this as a matrix, just a matrix, not a matrix whose elements are matrices. Just for simplicity, I erase the brackets and I see that this is a star matrix acting on this matrix here times the matrix itself. So this is a conjugation. So this means that phi M, by the previous thing that we've just proved, is positive. But this is true for any M, right? So this means that conjugations are a perfectly good example of completely positive maps, which is very simple and surprising. So this is good because we know that conjugations, in almost every algebraic sense, conjugations is a very good operation. Okay, these are very good maps usually. So it is good to know that they are also completely positive when we consider these spaces. Moreover, if we choose this matrix to be a unitary, this is actually a unital and completely positive map because obviously the image of the identity matrix is the identity matrix. Okay, so since unitary conjugation is probably the best map you can have between two vector spaces, right? Because unitary conjugation preserve, in the case of matrices, spectrum eigenvalues or positivity. They preserve the entire structure, almost every aspect you can think about. It is also good to know that these unitary conjugations are actually UCP, okay? Unital and completely positive. Okay, so I just want to say that we are now, the plan is to show you another very simple example of a completely positive map. To show you a very simple map which is not completely positive. I just want you to be prepared for what's coming. And then we're going to do some very nice and fun algebra. I hope this will cheer you up from all the rigorous proofs we show here. But we're actually going to deal with a very simple way to multiply two matrices and say what's the relation between this type of multiplication to positive maps. So, to get back to our talk, to the talk. So let us now define what is called a star representation. Okay, so a star representation, obviously it relates to the star operation of matrices. So this is any linear map which is also multiplicative. This is a very unusual definition if you come from the world of linear algebra. So it has to be multiplicative and star preserving, meaning that pi of AB is pi of A times pi of B, and pi of A star is the same as pi of A and then taking the star for any two matrices. So assume that I have some star representation. I want to prove to you in a very simple way that these are also completely positive. So, yes?
Didn't this one raise in algebra?
What?
Didn't this one raise close manipulation.
Right. So in this case, I want this this multiplication to be well defined, so we can talk about a certain algebra inside MQ. Okay, so star representations are completely positive. So assume pi is positive, then pi of A star A by definition is pi of A star pi A. This is pi of A star pi of A, which means it preserves positivity. So now I want to show that pi of M is also positive for any M, which means that it is indeed a completely positive map. So assume that I have a certain matrix of this form, and I want to take, I'll prove just the star operation because the multiplicativity is also very simple and it works the same way. So let's assume I take this matrix star, which means I put a star on each element and take the transpose. Notice that 1m is actually here instead of here because I took the star operation. So this is pi m of a certain matrix star. So by definition, I take pi to act entry-wise on each element here. But pi is a star representation, which means I can take the star out. And this means this matrix here is actually just taking, I can take the star, do the transpose and take the star out by definition, which means this is just pi m of this matrix with the star operated on it. So again, pi m is also positive for any m, which means, again, that star representations are also completely positive maps. So far, any standard positive maps we've encountered turned out to be completely positive. So we want to ask, is there any positive map which is not completely positive? So this really is the case. There are such maps. And let us look at a very simple map from the 2x2 matrices to the 2x2 matrices, which just takes A to its transpose. So obviously, phi is positive. If A is a positive matrix, which means I can write it as B star B, then phi of A is phi of B star B, which is B star B transpose. Now we use the properties of transpose and the star operation, which means I have B transpose, B star transpose. So I don't know why I needed this. Oh, and then the transpose and the star operation, they are commutative. So I can write it as this form, which means it's a matrix times a matrix star, which means it is a positive semi-definite matrix. Okay, so it is a positive map. But I want to show that it is actually not too positive. Not only it is not n positive for a certain, I don't know, big n, but even for n equals 2, it is not too positive. Because if I take this matrix here, can anyone tell me why is this matrix positive semi-definite? This is a very simple trick from linear algebra.
It has eigenvalues 0 and 2.
It has eigenvalues 2. It has eigenvalues 0. And it has also eigenvalues, I think, 1 or 2. Anyway, you can easily check that this matrix is actually it's actually a positive matrix. But if I act on it with phi2, and now it's important to know that, as we said, this matrix is a 2x2 matrix whose elements are 2x2 matrices. And when I act on it with phi2, I actually just do the transpose on each block. So this new matrix has -1 as an eigenvalue, which means it is not positive. Okay, so I take a positive element to a not positive element. So this is not a too positive map, which means it is a positive map which is not completely positive. Okay, so there are such maps. And it is actually, this map actually comes up quite often in quantum information theory, by the way, but I won't go into it now. If anyone's interested, maybe after the talk. Okay. So now we're going to the fun part. Imagine that in the first course of linear algebra, the lecturer would define matrix multiplication to be entry-wise. Okay, so the multiplication of A with B, it's just A11 times B11, etc., etc. Okay, so this could be nice, right? If this was matrix multiplication, linear algebra courses would be, I don't know if much easier, but much simpler for a new student in the academy. But actually, even though this is not the matrix multiplication we use, this product which is not, again, not our usual multiplication, is actually called the sure product of A and B. We denote it by A. This is not the same as A star. This is a lower star B, okay? And as the next theorem shows, okay, and be ready for it. The next theorem actually shows that this map is a very good map. Okay, what does it mean that it's a very good map? Let's define a map from Mn to itself by taking the sure product with a given matrix A. So the following are equivalent. If A, or not if, A is a positive matrix, if and only if this map, which I just defined from Mn to itself, is a positive map, and actually this is if and only if it is a completely positive map. Okay, so this very weird matrix multiplication actually turns out to be very useful and gives us a very nice way of producing completely positive maps.
Just a comment.
Yes.
Because you mentioned it, that it would have been nicer if we would have learned the matrix multiplication the way you explained. I would like to just point out that this matrix multiplication is also known as freshman matrix product. So of course it is of course in the reverence of sure that it is called sure product. But there is another name quite often
Freshman product.
Freshman product. Freshmen will do matrix multiplication of the same order exactly this way.
It's basically like the freshman stream for linear algebra, right?
Yeah, right, exactly.
Just a comment.
No, thank you. This is a very nice a very nice name. So we call it from now on a freshman product. Okay.
I don't know how much sure we'll be happy about that. Just a promotion.
Okay, so we are actually going to prove this theorem. It has only one technical, not very long, one small technical part, which is very, I think we can learn a lot from it, but most of the proof will be easy. Okay, so the fact that SA is completely positive obviously implies that SA is a positive map because complete positivity is also positivity. But the second part is actually very nice. So assume that SA is positive, and I want to prove that A is a positive semi-definite matrix. Okay? So let us take the positive matrix J. Okay, this is a positive matrix. Again, it has eigenvalues n because the sum of the rows is the same, and all of the other rows are also the same. So the eigenvalues are n and 0, which means it's positive definite. And this matrix, when I apply SA of J, I assume that this is a positive map. The image must also be positive. But when I take the entry-wise product of J with A, this is just A. Okay, so this means that A also has to be positive. Okay. And the last part is obviously a bit more technical. So I want to show you something very nice that I didn't get to work with quite often in the undergraduate studies, but now it is a very useful thing and a very strong tool. So I want to loosely define what is a tensor product of two vector spaces. Okay, so let us assume that we have two positive integers, n and m, and let us just, for the simple case here, let's just take a standard basis for each of them, for Cn and Cm. The space Cn tensor product Cm is just the space that is spanned by these nm symbols. I have, for each combination of I and j, I can take this element here, I can put a scalar in front of it, and I get an n times m dimensional space. Okay? So this is a very simple definition. This is just the span of these symbols here, which I did not yet here I give a more concrete definition, but these symbols, I just decided these symbols are the basis elements for this space. And I, yeah, I know. At first I wrote it as F, but I thought it might be confusing. But these are not the same vectors, right? This is a vector of Cm, this is a vector of Cn. Maybe it would have been better if I used a different letter for this. Okay, so if it's confusing for you, just assume that I have F here in the second element, okay, instead of E. So this is a new vector space. Okay, it is linear by definition because I just write it as the linear span of these elements. But I also want to define an inner product of this space. So in order to define an inner product, I just need to define it on such basis elements, right? Because by this definition, which means that this product with this product will be 1 if both indices are the same and 0 otherwise. This means that these elements here are actually an orthonormal basis for this new space. Okay, this is just by definition. So as the last thing I want to show with respect to this new definition, this new world we're working with, is that if I have a certain A which operates on this Cn, an m by m matrix, and B is an m by m matrix, I can define a new operator which acts on this new space. How does it act on the new space? We say that A times B on this basis element just acts as A on EI, tensor product B on EJ. And by linearity, I can then later expand it and see how it works on the entire space. Okay? So why define this tensor product of two spaces? So for now, I define a certain operator which takes us from Cn to the tensor product of Cn with itself. This is a very weird definition if I just throw it at you like this. But we will soon see why it is very, very useful and very, very easy to work with, actually. So I define V such that EI is mapped to the diagonal element, EI times EI, okay? So I say that this operator here, V star A times B, A is an n by n matrix, B is an n by n matrix, V star A times B, V is an operator which acts on Mn, on the Cn. How does it act on Cn? In order to do so, I just have to take its operation on these basis elements, and I get exactly the ijth element of this matrix, right? This is by definition. So whenever I have this star on the left side of the inner product, I automatically take it to the other side. There should be, okay, maybe I should have done it in 2 steps, but V on EI gives us EI times EI, and when I take this V to the other side, to EJ, I get EJ times EJ, okay? So this is just the adjoint property. Now, by the definition of these operator, these product operators, I act with A on EI, and I act with B on EI. And by the definition of the inner product, I take the multiplication of this inner product with EJ and this inner product with EJ. But this is for you, this is really basic linear algebra. What is this element? Okay, it's written here. It's not this is exactly the definition of the ijth element of the matrix A, right? So what I got is that the ijth, so this means, okay, this is not very important. I'll say it, okay. So what we got is that the ijth element of this operator here, this matrix here, is actually the same ijth element of the sure product of A and B, right? So this means I can present to you the sure product here as some conjugation with V of this operator, this product operator, okay? So we are now ready to prove the last part of the theorem. This is just a very important observation. This is why I defined the tensor space here, the tensor product. So assume A is positive semi-definite, which means I can write it as a S star S for some matrix S. We defined a product operator. I define a certain map which takes an n by n matrix B to the product, to the tensor product with I as a first element. Okay, so we talked about what it means. Actually, I won't prove it here, but this turns out to be a star representation. It is quite easy to check that if I take pi of AB, by definition, this is IN times AB, IN A times IN B, etc., etc. So this is actually a star representation. Okay, so keep this in mind. So if I take this matrix here and I want to take the entry-wise sure product, okay, so hang on, we're almost done, I promise. I know this is a bit rigorous, but this is the last rigorous part of the talk. So if I want to take this map and prove that it is positive, I assume that this is a positive map. And by acting on it entry-wise, I get a sure product with each element, which we can represent in this form, okay, for each element by the identity we proved earlier. Almost done. Okay, so now writing A as S star S, I can show that this is actually the map. This is another way to represent the map. And the last part, this is the last part of the theorem. You can notice that S times S is actually this weird product here. Okay, so why is it true? Because the star operation, okay. So the star operation actually acts entry-wise. So this is S star times IN. So if you multiply these three together, you get this. Okay, by definition. Just check me by the way I define these operator products. This is a very simple observation. Okay, but this means that we have something star times the representation of Bij times that thing without star, right? So this map can actually, I follow from this to write it as this certain matrix. I shouldn't have a V here, I think. There shouldn't be a V, this is just S star. So this is S on the blocks, right? Because I write it, there's this S star tilde and S tilde here and here with the kth representation of B. Okay, but this means that this kth sure product that we want to prove is positive is actually a conjugation composed with a representation. So as a composition of two positive maps, it is also positive. Okay, so note that the theorem, this is I think this is the fun part that relates a bit more to basic linear algebra. This gives us a nice way to check whether a matrix is positive. Okay, so for example, if I take this weird matrix whose elements are 1 everywhere except on the diagonal, and the diagonal has some number bigger than 1, I can write it as this matrix J that we defined earlier, right? With an addition of lambda minus 1, the identity matrix. So this means that D lambda is actually bigger than J. Why is it bigger than J? Because if I subtract J from D lambda, I just get this matrix, which is positive, right? So this matrix is positive semi-definite. Therefore, for any A, if A is positive, the sure product with this D lambda must also be positive. Okay? Okay. This means that if I multiply a diagonal element by some lambda bigger than 1, I preserve the positivity of the matrix. So for example, since this matrix turns out to be positive, we won't check it for now. This is not the most useful tool. I'll show a much more useful tool in a bit. But this matrix turns out to be useful, which means automatically that if I multiply the diagonal by 2, I still get a positive matrix. I don't have to check it. What's more surprising, I think, this is here as a side note, that because this map is not just positive, but completely positive, I can actually multiply blocks, the diagonals of each block, by a bigger than 1 element, and I still get a positive matrix. Okay, so this gives us a large families of positive matrices, which are a bit easier to describe. Okay, another very useful and another nice example is actually a necessary condition for a matrix to be positive semi-definite. So let us take the sure product with the identity matrix, okay? The simplest sure product possible. What does the sure product with the identity matrix do to a certain matrix?
Integrate the same matrix.
I don't get the same matrix, because if I take the sure product, everything becomes 0 except the diagonal, right? So if I take the sure product of IN with a certain A, I get a diagonal matrix. And the diagonal matrix is positive if and only if every diagonal element is non-negative, right? So a necessary condition for a matrix to be positive is that none of the diagonal elements are negative, right? So if I find the negative value on the diagonal, it is automatically not positive, right? So this is a very nice example, I think. And again, notice that we can actually use it to check block matrices as well, because if I take, for example, a 4x4 matrix, and I delete the off-diagonal elements from each block, if I don't get the positive matrix, the matrix itself was not positive. Okay, so as one final example, because I want to show why the Schur product is so nice to work with, and to show that it's actually very useful, even though it is not the formal multiplication of matrices. So let us take some m smaller than n, strictly smaller than n, for example, and denote by Jm the matrix that we worked with earlier, but only so that we have one on this block, only on this block, and everywhere else we have 0. So this is a positive matrix, right? Which means that if I take the Schur product with A, I get that this matrix here has to be positive. So this is actually something we're familiar with from linear algebra, that if not all of the principal minors are, if any of the first principal minors, any of the principal minors are not positive, then the matrix cannot be positive. This is actually very known from linear algebra. So this is another way of proving it, right? Because if this is a negative matrix, A is also not
there was
positive.
a question in the chat.
Oh, okay.
No, I'm on it. Okay. Okay, sorry. No, Guy Solomon
okay.
is just saying thanks for the great talk. Go ahead, Johan.
Thank you, Guy. Okay. So this proves, right? This shows the nice and quite simple uses of this Schur product and the fact that it is a completely positive map. Okay, next. So what we've seen so far is that the Schur product also turned out to be completely positive, but the proof was actually to show that the Schur product is a composition of a conjugation with a star representation. And the next, actually quite surprising theorem, which has much wider applications. It is also true for general operators on Hilbert spaces. So the next theorem by Steinspring actually proves that this proof that we've taken was not a coincidence. Okay, so let A be a unital C-star algebra. For our case, Mn is enough. Okay, so assume that we're dealing with a certain Mn. And let phi be a completely positive map. Again, assume this is Mn. For our example, it is enough. So so every such completely positive map has this property that there exists a Hilbert space, a larger Hilbert space K, for our case, some other bigger dimensional space. A unital star representation. A unital means it takes the identity to the identity, but a star representation that takes us from Rmn to this mk of some larger k, and the bounded linear operator, never mind the word bound for anyone who's not familiar with it, such that this map phi is a conjugation by this operator v with the star representation pi. So Steinspring actually proved that this is not just a coincidence. This is actually a characterization of all of such completely positive maps. There are no others. Okay, so this is actually a very interesting result. This is not very important for now. It is, but not for now. So again, any positive map from such C-star algebras like Mn to another operator space like some other Mk turns out to be a conjugation with a composition of conjugation and the star representation. So this sort of gives us a complete characterization of such maps, and this is very useful. So we've seen that completely positive maps, and actually more specifically unital and completely positive maps, are exactly those maps whose main property is order preserving, right? For the partial order we defined earlier. So now, after we know these properties preserved by UCPs or CPs, I want to say when two operator systems are the same in a certain sense. Okay, so now I want to define the equivalence class of such operator systems. So let S1 and S2 be two operator systems. Again, this is just a subspace which contains the identity and it is self-adjoint. We say that they are completely order equivalent, which is a very powerful word, I think, if there exists a bijection, a linear bijection from S1 to S2, such that phi is actually a unital and completely positive, and its inverse is also unital and completely positive. Okay, so in that case, this is the equivalent class this defines the equivalent classes of operator systems. So more specifically, because now I want to talk about something that relates to, well, my area of interest. If I take any D operators, doesn't really matter which. If I take two pairs of a pair of D tuple of operators, okay, I want to say when they define, in a certain sense, when do these two D tuples define the same operator system. Okay, so I can always take, this is an operator system right here, because I have the identity, I have the span of each element and its adjoint. So obviously this will always be an operator system, and this is also an operator system. So I say that these two D tuples generate the same operator system if these two operator systems are completely order equivalent, but we demand something else. We demand something a bit extra, that this phi, which gives us the complete order equivalence, actually takes each Ti to its partner, right, on the other side. So if this map turns out to be unital completely positive, invertible, and its inverse is unital and completely positive, we say that these tuples generate the same operator system. But why is this interesting? Okay, so we defined the new equivalence class, and we want to show that we can actually prove something and show something. So let us take a very specific case of an operator system, which is called the spin system. Okay, so what is a spin system? A spin system is just an M tuple of unitaries, okay? We also demand that they will be self-adjoint, but M tuple of unitaries, which are anti-commuting, okay? So for example, anyone who's seen these matrices knows what I'm talking about. These are the Pauli matrices, okay? They play a very important role in quantum mechanics, in quantum information theory, et cetera, and also in operator theory. And you can easily check that these are all unitary matrices. This is these three matrices anti-commute, and they are all self-adjoint and unitary. So an article that came last year, okay, by these wonderful people, actually proved something very interesting. If I have two M tuples of self-adjoint of spin unitaries, which means that they are unitary, self-adjoint, and anti-commute, they are automatically completely order equivalent, which means something I think it is quite surprising, that the complete order equivalence here is just to check whether these two are completely order equivalent. I just have to check the cardinality of this tuple. If I have M tuple here and then M tuple here, these are automatically completely order equivalent. Okay, so this is the same thing. And now I want to extend it a little bit. This relates to my area of interest and Shalit, obviously, which helps me a lot. So let us extend the notion. Okay, instead of anti-commuting, let us call such an M tuple. Let's say that it is Q commuting. If whenever I have these two matrices, they Q commute, which means they commute up to this scalar multiplication by some modulo 1 complex number, okay? So again, another article that came again last year, it came after the previous article, showed that if UV and U prime V prime, only tuples, notice that this is only pairs. If I have two pairs of Q commuting unitaries, which are of pth order, this is another thing that we demand from this tuple, so U to the power of P equals V to the power of P, et cetera, equals 1, then they are automatically completely order equivalent. So this seems like a much weaker proof, a much weaker theorem, right, in the case of Q commuting, because before we had this theorem true without the P order. And moreover, we didn't just prove it for. They didn't just prove it for two. They proved it for any M tuple of such unitaries. So unfortunately, for the case for more than two matrices, they actually found an example of such three tuples, which is not completely order equivalent. So the Q commuting unitaries rise naturally These operators actually are a part of a theory.
When you say piece order, you mean
This.
this is minimal.
Right, minimal, yes. So the Q-commuting unitaries actually rose from a certain quantum systems, and the operators which Q-commute, they form what's called a rotation algebra. So they came to be actually, they rose quite naturally in quantum mechanics and in the study of operator dilations. So if we can understand how does certain properties of these matrices give us information about complete order equivalence classes, we can actually learn a lot about many other systems, and it is still an active area of research. Okay. So this is it. Any questions?
Do you have an idea why we care about UCP maps in quantum mechanics, or is it?
Yes, in quantum information theory, whenever we have a certain density matrix, and we want to show how it propagates in time, the map which takes us from time t to time t1 is a completely positive map. It is actually also trace preserving, but it's a property that actually comes naturally. It is sort of the adjoint map of a UCP map. The adjoint map of the UCP map is a completely trace preserving map, completely positive trace preserving. So these are very important maps also there.
Both of these are non-structured channels by respective
Mm-hmm. Anything else? Okay. So
Okay,
thank you.
Thank you, everybody, for coming either on Zoom or in the classroom. And if anybody wants to give a talk about anything in the What Is seminar, then you can contact either me or Tali. Our emails are on all the posters, and we would like to hear what you guys would like to talk about. So thanks for coming, everyone.
Thank you.
תודה רן.
Bye-bye.
זהו, כן, אפשר לסגור.